Thanks for the invitation. Right, it's a great pleasure to give this talk here, even though remotely. Hope once things get settled down, I'll still have the chance to visit you guys in person. Okay, and today I'm going to talk about robust spatial perception in degraded visual environments. And the roadmap of today's talk is like this. So in the first part, I will briefly talk about the background about spatial perception and the visual degradation. Then in the second part of the talk, I will dive into the details of two represented works and systems in this domain. Then in the last bit of talk, I will briefly go over some other ongoing work related to the visual degradation and spatial perception, but at a high level idea. All right, let's get into the first part. So what is spatial perception? Well, spatial perception in a broad sense is a type of ego awareness when an agent is moving in the environment and would like to know where he is and what obstacles are around it, right? So purely based on the sensory data. And in the language of robotics or computer vision, such two problems are also called pose estimation and mapping. Both of them are quite essential to human beings if you really think about it. Like every day we go from our home to the school or the office, actually we heavily depend on our spatial perception ability. Well, spatial perception is a problem that has been studied for decades, but recently we are seeing two interesting trends about it. The first one is spatial perception now is deeply interwoven with emerging embodied agents, which is widely recognized as a kind of a key enabler to the successes of the embodied agents. For instance, a vehicle can be called autonomy if it doesn't have a clue about its location or obstacles around it. And similarly, an indoor AGV robot needs to navigate itself to the right entity or goods for manipulation and grasping. Of course, augmented reality, mixed reality devices are digitalizing our lives. But effective for human-machine interactions for such kind of a metaverse world relies on the heavy spatial perception of it. We need a better understanding of the user poses and the surrounding environments. Lastly, we can't forget about the UAVs, which is heavily find applications in spatial exploration as well as city-level surveillances. All these kind of applications will depend on a good spatial perception system. Besides a both trend for the application domain, we're also seeing a technical trend happening for the spatial perception. Let's take the SLAM as an example, which stands for simultaneous localization and mapping. That's a short name for SLAM. SLAM is arguably the most progressing field for spatial perception, and we can find from the left diagram that spatial SLAM is still heavily dominated by the optical sensors such as stereo camera, RGB camera, LiDAR, and depth imaging cameras. Those are typical optical sensors. And no matter it's about a single sensor SLAM or it's about a multimodal SLAM, still optical sensors has a heavy and strong roles in the success of them. Well, we know stereo optical sensors are very ubiquitous. They are becoming very low cost these days. But the problem here is that these sensors are not always reliable and can fall short when there is a visual degradation. So what visual degradation we are talking about, and is that significant? Well, interestingly, there's no kind of official definition about the visual degradation in Wikipedia or textbook, but broadly it refers to any conditions that can degrade the performance to the optical sensors, or this degradation can lead to high consequence failures. Actually, if you really think about it, such as kind of a degradation is very common in both benign environments like everyday life or extreme conditions. For instance, you may hear that many of Tesla accidents are due to the visual degradation. Since like white trucks from the white sky, Tesla just can't differentiate this kind of white object from the white sky due to the contrast limitation for the visual systems on the car. Well, there are also kind of many sensor manufacturing and constraints. Optical sensors-based perception is still very fragile in both bad weather, outdoor, or even for some transparent objects in indoor, because we know this kind of optical sensors will just see through these transparent objects without really treat them as obstacles. All these kind of things are big problems for spatial perception. Well, when visual degradation issues come to the more extreme conditions, this problem becomes more prevalent. So in an underground tunnel, spatial perception is always challenging issues, as everyone knows here, right? Because of the repetitive patterns in that tunnel for both layouts and appearance. And if we further consider exploration over caves, maybe in the outer space, which is regarded as the most suitable shelter for the human space migration, then the coupled illumination and the repetitive patterns will only make the problem even more complicated. In an analogy, it's pretty much place oneself into a maze without giving that guy any lighting sources. That is totally a disaster for any kind of spatial perception systems, no matter it's about mapping or it's about localization. And lastly, we can't forget about some use cases of the firefighters in the smoke field situations for emergency response, or maybe a worker in the construction sites facing the dust field environment. All this kind of challenging situations is all linked to visual degradations and make today's spatial perception systems, more specifically, very fragile and fall short. So after understanding the visual degradation and its impact on spatial perception, this talk, or actually the majority of my research, is trying to answer the following question: how to let embodied agents, either for a mobile robot or intelligent wearable, robustly obtain the spatial perception information in a degraded visual environment. Of course, one can always argue that robustness can be achieved by improving the existing algorithms designed for those optical sensors. Well, I can't say it's wrong. However, such improvements are not fundamentally robust because optical sensing limitations are physically intrinsic. I therefore argue to solve this problem following a more cyber-physical approach. We start by finding the right sensors that can be intrinsically robust to visual degradation, and then try to find the right algorithms for that specific sensor. Well, if we look at the left diagram here, which is a spectral, electromagnetic spectrum, and we'll find that optical spectrum or optical band only occupies a very small portion of it for the visible spectrum. But the whole right side about that, which is very low frequency, but with large wavelengths, is heavily unexplored. But this whole website also enjoys better or larger wavelengths and can see through smoke or deal with any visual degradation, which is intrinsically robust to the situations we are had a headache about it, right? So in this sense, my research actually heavily used different unconventional sensors in this kind of a band, ranging from the thermal cameras, which is infrared band, to the mmWave radar, which is has a larger wavelength than the infrared sensors, or very low frequency electromagnetic Powerline sensors. So all these kind of sensors, although it's not conventional, not ubiquitous, but it also brings a lot of interesting angles to solve the problems we are out of our hands. So after identifying the right sensor, the next step is to find the right algorithm for them. But compared with the data from the optical sensors, the data from these unconventional sensors is very different and can be quite complicated. I'll definitely show you some concrete examples in the second part of my talk. But at a high level, the data from these sensors are very difficult to interpret from our naked eyes because our five senses doesn't use such a kind of sensing modalities. So we can't relate ourselves to the design. In the meantime, these sensors data are quite noisy sometimes or sparse that can be very difficult to formulate sufficient design heuristics. So as a kind of alternative, my way to solve these problems or leverage the power of the sensors is to heavily embrace the data-driven methods, either it's from the deep neural networks or the more general data-driven approaches. Another benefit of this kind of data-driven approaches, besides directly or automatically find the value in this kind of data, this kind of sensors can be treated as a subnet or a branch of the neural network of the entire model. Then if you want to jointly optimize the sensing branches collectively, this kind of a end-to-end or back propagation will just make the problem so easy. So you don't need to worry about what's kind of the best synergies between the sensors. Okay, that's pretty much the design rationales of my research. And guided by this kind of rationale, my past work has touched upon almost every component in a spatial perception pipeline, from the pose or odometry estimation to mapping to localizing and the entire SLAM systems. But due to 10 minutes, I guess today I will only focus on these two representative works. But if you are interested, you can feel free to contact me to get understand about the other works listed here. And in the last part of my talk, I will show some cool demos for some works. I don't have time to elaborate. All right, now let's enter the second part. So let's start with the first work. The task here is try to estimate the Egomotion from a series of sensory data. And to date, visual inertial odometry is still the most predominant solutions to this task. Namely, one can combine the multimodal data from a camera and from the inertial sensor to make it a very good, kind of odometry estimation systems. Even use Kalman filters or extended Kalman filters. That's kind of very typical ways. And of course, you can use deep neural networks to do that. It's just up to you to pick the right algorithms. But the sensors are almost fixed to this too. But as we know, inertial sensors, they are cheap. They rely on the inertia without bothering using the external sensors from the environment. So it's safe to visual degradation. But we also know, as I described before, optical sensors, they are not good candidates here because they can't deal with lots of illumination or airborne particles such as fog, smoke, and something. So our mini ecosystem was proposed in this context. And we try to find robust and inexpensive solutions to handle the above visual degradation without sacrificing the Egomotion estimation performance. The key idea behind this work is a novel sensor fusion system, featuring the single chip millimeter radar to replace the optical sensor in the original system. Well, to understand the mini ecosystem better, let's first have a look about the working principles to the radar, which is also the focal point for this work. A millimeter radar, or radar in short, is a transceiver device operating in the spectrum between 30 gigahertz to 300 gigahertz. It works by transmitting the FM-CW wave to the surroundings, and the transmitted wave can be reflected back from the objects in its field of view, and received by the radar again. Then the radar, by mixing the transmitted and received signals, the device can estimate the distance and orientation to that object in the field of view. The objects are often represented in the form of point clouds because of its larger wavelengths in millimeter. This kind of a radar can be very robust to airborne particles and impervious, almost impervious to any lighting conditions, which is exactly the property we want to have for our system. And what's more worth noting is that, driven by recent advances in nanoscale CMOS technology and miniaturization technology, today's radars have emerged as a low-cost, low-power, and single-chip solution. Compared with LiDAR or the mechanical radar, which are kind of ancestral radar, we call that, used decades ago, such a low-cost sensor is more lightweight and able to fit the payloads of a lot of micro robots, if you think about the drones or more wearable devices. Actually, today we have already seen this radar appearing on smartphones, such as Google Pixel 4 recently embraced such a single chip radar on the smartphone for battle sensing, and lots of kind of automotive vehicles, such as Ford, Uber, even Tesla before used this millimeter radar for battle sensing. So this radar sounds like an exciting opportunities ahead of us. And the data format of point clouds is not something we are not familiar with, right? Point clouds are just already established. representation. And lots of algorithms have been proposed to deal with it. But along the way of cracking it, we soon realized that transforming the radar data to use for Egomotion estimation is much harder than we initially expected. To understand the technical challenges here better, let's first see how Egomotion was conventionally estimated from consecutive point clouds. So at a high level, this kind of a pipeline consists of two steps. First, point matching. Second, transformation estimation. Point matching aims to find the kind of a transformation of separately acquired views by maximizing the overlaps or overlapping points between two frames. Then, given the matched 2 point sets, the relative poses or transformation between the frames can be easily estimated by solving an optimization for the best alignment. So all these kind of methods are well established. Let's say the ICP is kind of a typical method in this domain. And plus ransack, you can also have some outlier rejection performance after that. But if you think about it, about this pipeline, you'll find something is not right here. So intuitively, the accuracy of the final estimation for this pipeline will heavily depend on the first step or the precision of point matching. And if you fail in correspondence or point matching, then no matter how good you are for the optimization step, you are just there. You won't have a better performance than it sets a bound for you, right? That's kind of the typical problems for this pipeline. When the data is good, it's fine. You have a lot of correspondences, and you can use ransack to reject outliers. But for our case, let's see what kind of a point clouds we are talking about here. You know, radar is low cost, it's small form factor, right? As we say, the single chip solution. But due to the specular reflection, diffraction, and the significant multipass effect of this millimeter wave band or millimeter wave signal, the radar data are corrupted by noise a lot. Our studies indicated that it can be 75% of the points being the outliers when you have some narrow corridors in indoor environments. This is too much for the aforementioned two-step approach because it's very difficult to find good enough matches if you have such amount of outliers. And to make the problem even more complicated, because of the hardware constraint and the low-cost design, you don't have a lot of massive MIMOs, let's say, for a single chip solution. Then the resultant point clouds are highly sparse and in low resolution. For instance, with the sensor used in the work I'm going to introduce, objects less than 15 degrees are easily merged into single point without giving you enough angular resolution. So all this kind of challenges seems not easy to solve, right? If you really want to get a Egomotion estimation system to work. And let's see how realistic it is and how real impact it gives to the matching results. And here I want to show a result that given the same thing captured by the LiDAR and a co-located radar, namely they have seen the same thing. Okay, then the matching results of radar is very unsuccessful, as we can see on the bottom right, and it actually has line-fold worse post-estimation error than the LiDAR counterparts. This is not a trivial number if you really think about it. But still, we want to address it, right? Because it's quite promising to deal with visual degradation. The problem here is like, do we still have a chance? Well, addressing the above challenge requires definitely the techniques beyond the geometry heuristics and the two-step approaches. We therefore argue and propose to use a data-driven method here, where the crucial to our design is a deep neural network that can allow for end-to-end models without considering the interleaving kind of a matching and estimation steps. We want to do it at once. So the lock-on effect between these two steps can be largely mitigated because we jointly optimize it, right? And here, let's talk about what kind of a radar network we are using here. Start with inputs. Because 3D point clouds are very unstructured and irregular, which is not friendly for neural networks nowadays that can be effectively give you something useful. So we first convert these point clouds to depth map. Note that here, this step doesn't incur any information loss because all these kind of 3 parameters, X, Y, Z in the point cloud world will just be reparameterized to the UVD, where D is the depth and U and V are just a horizontal and vertical kind of axis there. So it's just to make the data more structured, then it can be easily or more amendable to the convolution neural networks. Then after getting that converted inputs, we use a FlowNet-like convolution encoder to extract the Egomotion features from the depth map. The reason we use this structure was heavily inspired by the great successes of it in predicting Egomotion from consecutive image frames. Actually, it's not our contribution. So if you are interested in this FlowNet-like neural network, you can go for their work to find the rationale for the design. That is really a good read. I highly recommend any interested readers should go for there. Okay, so far we somehow find a good way to introduce and design the encoder for the mmWave data, but the job is not finished. And the question remains is how to maximize the fusion synergy between radar and initial sensor in the network model, right? Don't forget, what we're talking about here is a multimodal odometry system rather than single modality. Well, I guess everybody's on board. A common sense to robust multimodal estimation of multi-sensor estimation is based on the premise for the complementary actions among different sensors. It's quite intuitive, and I guess everyone is not against it. The roles of different sensors should adapt to be altered in response to different situations faced by the mobile agents. For example, the radar sensor should dominate the Egomotion estimation or tone up when there is a MU degradation on a bumpy road, let's say, and vice versa for radar when it itself has some problems for some crazy turns, which is not a sweet spot for any radar or imaging kind of sensors. However, although this kind of rationale or this design intuition is clear, it's not easy to incorporate such a well-defined concept into a neural network model because it's black box. Everyone knows that, right? How can you imagine you can manually incorporate some very rational stuff into a black box model? And more importantly, the problem at large is that even we do have multi-sensor fusion deep neural networks today, these networks are still dominated by this kind of thing called single-stage attention mechanism. But such methods merges the heterogeneous sensor features very early. That simply treat the problems as a parameter reweighting for the neural network. And as a consequence, more often than not, we can't see the complementary behaviors between our radar and MU sensors. But they exhibit the simultaneous changes, let's say, simultaneously tone up or tone down when some situations happens. We don't call this as a complementary behaviors among the sensors. So can we make the sensor behaviors more complementary, even in a deep neural network? Well, our solution to mitigate this problem is inspired by a famous psychology model proposed by Charles Spence, who was kind of a quite famous psychologist in Oxford. It's a very dense work about that kind of validation and experiment. But at a high level, Spence's team validated a 2-stage model when we human beings perceive the spatial environments using our 5 senses. So in his theory, and also got validated, the first stage, our auditory, visual, and tactile systems separately function in cognitive recognition, without interleaving with or interfering with each other. And only in the stage 2, another part of our brain will do the fusion job and make the fuse different modalities after processing together to finish the whole pipeline. Of course, this is a very high-level explanation for that book, but it doesn't affect our design. So inspired by this theory, we propose a 2-stage mixed attention model, which is quite different from the previous one. And the key difference against the prior art is the order between attention and feature merging, as well as the inclusion of a new layer called cross-modal attention. In particular, we first perform the self-attention on individual sensor features without any interferences. Then we only generated the cross-modal attention masks in the second stage. And only when two-stage attention is complete, the multimodal features can be finally merged. Noteworthy that here, I just use examples of inertial sensor and mmWave radar. But our framework can easily generalize to 3 or more modalities even. You can find how we achieve this in our paper. And on receiving the fused multimodal features, the recurrent neural network is subsequently tasked to model the long-term dynamics. We adopted the recurrent neural network here for its proven ability in maintaining the memory of hidden states over long run, which is crucial here because Egomotion is quite related to the dynamic systems if you think about it. And given the output of the elements, fully connected layers are finally introduced in the end to regress out the 6 degree of freedom features, namely X, Y, Z, row feature, this kind of relative motion. From these features we got from the network. And that finished the pipeline of mini-ego. So let's see some evaluations. 2 multimodal sensing platforms were implemented here, one for mobile robot and one for handheld devices we prototyped. For the robot platform, we use a total of 2 equipped with mmWave radar, IMU, RGB, and depth cameras. Here we use a lot of sensing modalities just for comparison, but still, mini-ego is just what you saw previously. The LiDAR here is used to provide ground truth because in the wild you don't have a good Vicon systems or motion capture systems. You have to rely on LiDAR to provide you some Egomotion truths to evaluation. Then for handheld devices, we design a 3D printed model that uses the same set of sensors. All the sensors are synchronized with ROS or robot operating systems here to make the data collection. And our test beds is quite diverse because we explicitly chose in this way to deal with a common criticism for deep neural networks about the generalization ability or overfitting, in a different way to put it. So to this end, our dataset consists of 17 distinct floors from 6 different buildings, which is quite diverse enough. I would say it covers most of all standard rooms in a commercial building you can think of. And this including, actually including the trajectory of 8 kilometer data. So it's definitely not a small data set if you take this kind of distance into account. And for baselines, we included both conventional and deep learning based methods to make it fair. We compare mini-ego with IMU ICP, which is a traditional fusion method that uses IMU to bootstrap the point matching of the radar, then added by extended Kalman filter to finish it, which is very standard and the traditional way. We also compare with other state-of-the-art multimodal deep odometry with different sensors, including the VINet for RGB cameras plus IMU, as well as a variant of DINet, which uses depth imaging camera plus this IMU. So we have enough diversities of the baseline in terms of the sensing modality. Now let's see some real results. This is just a glance of all the trajectories we did, right? So the blue line was generated by mini-ego, namely the method proposed by us. And actually we found it only has around 1%, almost 1% drift error, which is actually 1 order of magnitude better than the second best approach here. It's actually quite a large margin. One reason is that in our environment, it has a lot of visual degradation, which I will show very soon with some demos. Another interesting result I want to show is like even without MU, let's say, why not just using the radar, right? We found that our result is still much better than the traditional methods like the ICP and teaser, which are quite established method for traditional Egomotion estimation with point clouds. Also, if you can afford 3 radars, let's say 1 front radar, 2 side radars together, then this kind of a synthetic wide angle radar is able to give very competitive results, even better than the depth cameras in some cases. Unfortunately, still such kind of single model solution is still not comparable to the radar IMU solution, because IMU is quite unreplaceable for such a motion-driven task. Now let's see some demos. You can know what I'm talking about, visual degradation. The first one is a mobile robot traveling in environment with a lot of glasses or these transparent objects, as you can see here, right? And on the right is a trajectory estimated by mmEgo in blue and the ground truth in gray lines. On the left, bottom left, we see the weights of different modalities. And you can see in some occasions, one sensor will tone down and the other tone up, because let's say sharp turn, which is a sweet spot for IMU, so IMU should tone up. And likewise, when IMU has some more function on the bumpy roads, the mmWave radar will take over. This is some complementary behaviors we talk about, and we definitely want our systems can automatically make this weight changing about these tones when different situations happen. Let's see, another situation is complete darkness, almost complete darkness, in a dark room. And here we provide some more camera footage just for visualization, but we didn't use it for estimation. Again, the blue lines of our mmEgo is quite close to the gray ground truth. In contrast, the best computing approach, we are not here struggle a lot to even recover the shape, right, of the movie. Last but not least, let's show a handheld device kind of experiment. In particular, we do this experiment with unseen user. That means the user is not in our training data set, and an unseen scenario. That means no data from this building or from this room was collected in our training sets. So to the neural network model, this is brand new. Again, we see the trajectories is almost right. Although we do observe some gap, let's say here, there's kind of a gap. But if you really think about the trajectories of these two things, right? The green one is ground truth, the blue one is our method. Then you'll find that our result is still quite promising, right? And if you have a let's say another module called the map matching or loop closing, let's say make it an entire SLAM system, then such kind of a gap can be easily mitigated. You can almost get the identical trajectories in the end. And more often than not, for such kind of a grade, trajectories is already enough for 5 adults, because they don't need to know 100% trajectory about themselves, but the coarse grained estimation. All right, last bit about mmEgo is runtime efficiency. Due to the intrinsic sparsity of the radar data, mmEgo system is able to efficiently estimate the motion at the frame rate about 17 FPS, even on an embedded GPU. In our case, it's a NVIDIA TX2. This is actually quite powerful, because if you use this kind of FPS rate, it's already enough for a lot of downstream tasks, even without the offloading kind of computation. Okay, I guess that's about the Egomotion part. And let's dive into the second part, which I will not dive into that detailed, but still quite interesting about the mapping. So in this part, we care about the other bit, about the obstacles in the ground, in the environment. And in particular, I want to briefly touch on the motivations behind it. That was because when I was a postdoc right at Oxford, some 5 others come to us saying, okay, we do found the need for an accurate map for safe firefighter operations, because lots of accidents of the firefighter tragedies are due to the lack of awareness in the fireground, which is full of smoke and lots of hazards in that environment. But if you think about the mapping problem, an up-to-date map or accurate map of the environment is very difficult to get, even in benign cases, not to mention, such a fireground cases where the, environment can change or be dynamic every second since just falling down due to the fire, right? And sending the firefighters as the first batch of people to get the map, you can do that. That is too dangerous and risky. So what we thought at that time is, okay, is that possible? We can send a mobile robot that quickly surround or survey the fireground and send a map back to the firefighters outside. Then the firefighters can get that map to make better decisions. Of course, it's not entirely real time, but still it's relatively fresh compared with the outdated one. right? And in this way, the motivation is also a motivation our next work called the mini-map, which is a sister work of a mini-ego we just saw. Considering the radar can provide ranging information and see-through smoke, it's not surprising for us to think mounting it on a robot and drive into the situations, quickly map the environment. Ideally, it would be better if we can not only get the magic map of the environment, but also get the semantics about the more obstacles in the ground, which can give you a more safe notion or semantic notion for firefighters. We do have both in our work, but due to time limits, I will just focus on the metric map reconstruction in this talk. Okay, let's have a look about the technical challenges. I won't repeat myself because many of the challenges here are overlapped with the mini-ego. Let's say the noise, high degree noise, and this kind of sparsity. And you have to remember that for mapping, the multipass noise is quite prominent. And if you can't just say, let's stitch lots of frames together to make the sparsity go. No, it's not like this because you still have the noise issues, right? And if you do so, the map is almost unusable for firefighters. And that's kind of the unique challenges here we want to deal with. Another thing is like this time, you can't rely on MU anymore. Because I said, MU itself is not the exteroceptive sensor. It doesn't imagine or get any kind of external information from the environment. So this time you just have the radar. And to solve this challenge, and inspired by recent advances of the image sampling, we consider casting this indoor metric reconstruction problem into a problem using the conditional generative GAN neural network, which is an architecture achieved a lot of successes in image upsampling. So if you think about the image upsampling and map reconstruction, shows a lot of similarities, right? So it's not surprising to think use their methods to solve our problem. And meanwhile, to cope with the labor shortage issues, we try to adopt a cross-modal supervision learning method here. We adopt this kind of network inputs still with radar point clouds. But for the labels, we actually leverage the LiDAR scans, which is co-located on the same robot, but only in the offline training phase. And when it comes to the online inference phase, we can't use LiDAR because LiDAR, as we said, is still optical sensors. It can't see through smoke. And we will ask the radar to use the learned model offline to do the online inference. That is kind of the rationale here. There are quite some technical details behind it, but I just don't want to dive into that technique things. And you are encouraged to have a look in our paper. Okay, network model is what's trained to reduce the kind of generated radar signals and the LiDAR supervisions. We try to reduce the difference between them or the discrepancy between them. So what total loss do we use to train the network here? At a high level, our total loss can be interpreted from a Bayesian perspective. That means our task of learning is to maximize the posterior probability of 3 types of classes for each pixel of the radar generated data, namely free, occupied, and unknown. This is just the 3 classes of labels, but if you have these 3 accurately, you can have a very useful grid maps for lots of subsequent planning and navigation tasks. It's a great word anyway. And for likelihood, we follow the previous works and incorporate the losses such as secant loss, intermediate feature matching, and the low power geometry, which are very standard. But one thing which is not standard and proposed by our work is try to injecting the map priors into the construction. Because all in all, what do we try to reconstruct here? It's not images, it's a map. And when we talk about map, and very useful prior about map is inspired by the commonly used Manhattan water model. So as the name suggests, Manhattan water model is grounded on the regularities of the scene statistics and assumes straight lines in most parts for a map, which is quite reasonable if you have a map of the city Manhattan. That's just lines after lines, right? And recently studies also reveal that even for indoor floor plans, we do have a lot of similar design rationales about lines, because we want to make things easy and regular. And this is quite a good thing for us to think, because if we can somehow capture these straight lines or seeing regularities as a map prior, we can only make our prediction much better and more efficient. Here, we achieve this by injecting 4 line detectors as a form of convolution operators with fixed kernels, each well corresponding to the lines in different directions. We have the vertical lines, horizontal lines, and some cross lines. That's just different lines we want to cover for the generation. And as we can see here, with or without injecting the map priors, we will have different reconstruction results for even single patch here, right? Let's say here, if you don't have the prior loss, you can have a lot of artifacts, and the lines of the corridor is just not as straight as we want. But after injecting that losses priors, we get a much better, much straight lines for the reconstruction. And if you can stitch multiple patches of these reconstructed ones, then you will have the 4 planes of the map, which is essentially what we want for the metric reconstruction. Okay, let's see some results. We compare with our methods to a wide range of baselines, including the traditional mapping methods with line fitting, as well as for different neural networks that has been heavily used in image and map reconstructions. As you can see, our methods, no matter what metrics you want to use here, either L1, which is the smaller the better, or the intersection of Euler metric, which is the larger the better. Still, our method consistently achieves the best performance against all prior arts of baselines. And here, let's see a demo to visualize the library. And this one, we reconstruct the radar raw scans patch by patch. And as you can see, without the reconstruction, the radar is something but too sparse and too noisy. And we also did this experiment in a cross building, which is a building was now seen in the train model for the generative testing, right? And still, we see, although the performance was not perfect, but the results is quite close to the ground truth here. If you consider this is an unseen building, then it's quite remarkable to a lot of use cases here. And we also did some smoke tests here, but unfortunately, it's for smoke, so the video footages was not quite informative. Instead, I just showed this kind of static images to show the corridor here. As you can see, all the optical sensors, RGB, depths, and the LiDAR, they fall short, they struggle a lot. The raw mmWave radar data, they are something. They are not affected by smoke, no matter what density we are talking about here, but they are just not useful enough. And after applying our mini-map system for the reconstruction, we can get a very good corridor reconstructed, which is very close to the ground truth we see on the left. Okay, I guess that's pretty much the main body of my talk. And in the last bit, I'll just use a couple of minutes to quickly go over some works related. A very related work I don't have time to elaborate, unfortunately, is a thermal inertial scan. And it has same goal as mini-ego, though the sensing and the perception pipeline is different. The question you may ask is why thermal cameras, right? If you have the radar. Well, by capturing the radiation emitted from objects, thermal cameras can function also very well under the darkness or heavy smoke. And if the temperature field is distinctive enough, thermal cameras can embed sufficient semantic cues about the environments in the captured images. But such kind of thermal cameras also come with a lot of challenges, like lack of robust features compared with RGB cameras, low contrast and long uniformity corrections. All these kind of problems cause practical issues if you want to use this modality to do some Egomotion estimation. And to mitigate the above challenges, actually in our most recent work on transactional robotics, we came up with a cross-modal plus multimodal fusion strategy. In offline, you'll find that it's quite similar to the mini-map, because we want or enforce the thermal cameras to learn from a co-located RGB cameras in benign cases. Benign here means no smoke, no visual degradation, everything is fine. And after the offline learning phase, we will ask the RGB cameras to independently work for the online Egomotion inference. Of course, we also have MUs, which is very similar to mini Ego, like the radar plus MU. Here is just thermal camera plus MU. Though the fusion kind of tech details are slightly different, but the philosophy is pretty much the same. So I will just skip the elaborations. Another thing is about neural loop closing of that. I won't dive into detail, but the key thing here is we actually develop a bespoke descriptor for thermal images when you want to use it for loop closing. Namely, try to find, is this a revisit the position that a robot has come before, which is pretty important for SLAM systems. And this is actually what we achieved in our works. And here I show two quick demos about it. First, on the firefighting drilling trials, which was in collaboration with US firefighters, and a DARPA subterranean environments, which is underground tunnel environments. Let's see the first one. So in this video, we have the green kind of ground truth. It's not perfect ground truth, it's just the UPT, but it's already what we can have in the best way. Also, we have our brown, it's kind of red lines, of our DPTIO, which is just the odometry part for this case. And we did this experiment with the firefighters, real firefighters in the United States. And as we can see, compared with the UPT, our DPTIO estimator is also very accurate. I would say it's pretty much close to the green lines. And as reported by the firefighters, actually the red lines here is more accurate to their working trajectories if you take this kind of scale into consideration. Also, we did a more complicated environments in the subterranean environments. It's very challenging because this tunnel environment is very repetitive in terms of the appearance and layouts, so you can't rely on good visual features for tracking. Here it's still very bright, but later on you'll see the lights will just be gone. Also, we have lots of kind of it's a very long trajectories. Actually, this whole data collection was in hours. So the whole trajectory is, even for this single trip, is in kilometers, which is quite long for any SLAM systems, I would say. It's a very long video. Let's just drag it a little bit to the middle part here. Right, that's as you can see, even at this point, we can start to see some drifts about the predictions, but previously it was very close to the ground truth. And even after the final trip, you can see here, now the robot is coming outside soon. Such kind of a recovery of the post-estimation results is very remarkable and can be useful in a lot of situations. And note that here, we just use thermal cameras and inertial sensors. Okay, last bit, I want to talk about that besides this kind of extreme conditions you just saw or indoor environments, my research is also touch upon the autonomous driving situations. As in this case, we use the radar to replace visual cameras, RGB cameras, for the place recognition, which is kind of a topological localization in the city. And the rationale here is like, raindrops will block the lens of a camera, but for radar, it's pretty, doesn't impact a thing to the radar, because the radar is impervious to the weather conditions. And our idea is, why not use it for place recognition? And our recent ICRA 2022 paper validated this and actually proposed a very effective place recognition systems by simply using the single chip radar on the automotives. And as we can see here, the green dots meaning the correct predictions, and the red ones means wrong predictions. Even it's a rainy day, even it's kind of difficult situations, we still got the most predictions in green, meaning correct. And this is actually, I would say, the first single chip radar-based place recognition work today. Also, the code is open source. Please feel free to try yourself. And another kind of sibling work also in ICRA this year was, we try to solve the Doppler effect for the radar, because it will affect this kind of a range measurements of such sensor a lot. If you think about, Doppler radar will definitely be affected by Doppler, right? It's quite intuitive. And our idea this time was not using deep neural networks, but try to explicitly model the Doppler effect in the ranging process and correct this, corrupted points by the Doppler effect. to make the scans more neat, more clean, and can give you better metric localization results. Again, we show this kind of experiments in real autonomous driving car. And after our method applied, the blue lines, which are our method, can give you much better results than the best computing approach, which was in red. And if you can see this in the dark environments, let's say, our lines always be close to the gray ground truth, while the red computing approach struggle a lot, to follow this kind of trajectories. And this is a really kind of a nice properties we want to achieve in future degradation environments. This one is in the rainy day. Okay, I guess that's pretty much of the demos I want to show here. Okay, last slide, I promise you, is a Powerline. It's a kind of crazy idea. I just I'm too excited to not to share with this. It's first time we show that Powerline. We know that it can be used for providing electricity, right, in indoor. But what you may not be aware is that such kind of a built-in power networks can also be used as a localization modality. Because of the alternating currents in it, right? The built-in power lines can somehow form a special electromagnetic radiation field. And as you can see in this video, if you have the right sensor, which we built ourselves, then you'll find that in different locations, the power line fields will exhibit different signatures, which are natural location sensors you can use for loop closing, right? And we actually do this for fields, this kind of loop closure with the power line signatures. I guess it's the first time ever to prove Powerline networks can also be used for localization. I believe there could be a lot of applications around it. Okay, that's pretty much of it. As a conclusion remark, actually, today I just showed my work in the degraded visual environments. But there are also a lot of other adverse factors considered in my research, such as malicious force from the attacks, how it will undermine the robust spatial perception, or some resource limitations, maybe on the resource constrained embedded devices. Overall, my research is trying to develop robust spatial perception systems by leveraging cutting-edge AI, IoT, and robotics technologies. And if you are interested in collaborating with any of these streams, please don't hesitate to drop me an email. All right, that's it. I'm happy to take questions now.